just how we have the constant pi, which is a very long, what's known as irrational number. So it's what, 3.14 blah 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 blah, and it just keeps going, right? E is similar. E has a value of 2.71828 blah blah blah, and then it just keeps going on and on. So there's a type of function, exponential function, which is e to the power of x. So it's taking that constant, raising it to the power of x. Now, the e to the power of x function still looks like a standard exponential. It's still going to go through 1. What they're going to ask you to do is, 1, they can ask you to transform this graph. So they could ask you something like y equals e to the power of 2x, for instance, and get you to draw that. Or they could ask you to differentiate an e to the power of x function. We're going to go through both today, or in this video, shall I say. Now, the transformation, you're going to use the same process of deduction, process of figuring out what to do, as with transformations we did before. So if we make fx as e to the power of x, with e to the power of 2x, you are essentially doing f2x. Yeah? So the notation is 2 times x. But if you remember the set of rules and the questions that we ask ourselves, the first question is, are we affecting x or y? In this case, we're affecting the x coordinates. Are we going to listen or do the opposite? Because we're affecting x, we're going to do the opposite. So if the question wants us to times by 2, we are going to divide all our x values by 2. The y value doesn't change though. So if we draw e to the power of 2x, it's going to look something like that. Let me draw that a little better, hold on. There we go, like this. So this would be y equals e to the 2x. And this one's y equals e to the x. So the process and the way you do the transformations is exactly the same as we've done before. The differentiating part though, let me explain that. If you have y equals e to the power of x and you differentiate it, you get e to the power of x. It stays the same. However, if you have e to the kx, you now get, let me draw this a bit better, hold on, k e to the kx. There's no minusing from the power with exponentials. Let me rephrase that. There's no minusing from the power with e specifically. There is multiply, there's no minus. So let's say if I have y equals e to the 3x, if I differentiate that, I get 3e to the 3x. I don't minus this number or this part of my function. There's no minus 1 that happens here, and it wouldn't become 3e to the 2x either. It would just remain as 3e to the 3x. Okay? So I've put up 4 questions I want you to try and differentiate those for me, please. Okay, B. We've got e to the power of minus a third x, and we want to differentiate. So we times by the power, and then we write whatever's left, or whatever was originally there. So in this case, I'm still following the ke to the kx rule, where k is minus a third. Okay, C. 7e to the power of 2x. You do 7 times 2e to the power of 2x. So you end up with 14e to the power of 2x. You're just timesing by the times in the number in front with the power. The number in the power. Next one. We would get 3e to the 3x plus 2 times 1 is just 2. So 2e to the x. Okay, F. With F, you want to expand the bracket first. E to the x times e to the x would be e to the 2x plus e to the x. That's what you get after expanding here and there. E to the x times e to the x. Remember, when you multiply, you would add the powers. So you're essentially doing x plus x, which is 2x. That's how I got that e to the 2x there. Now you're ready to differentiate. 2e to the 2x plus e to the x. Cool, that's differentiating done. Now, 2 questions for the sketching of graphs. I want you to give those a go if you can, please. Okay, how did that go? Let me try E with you first, and then if something clicks, maybe give F another go. 6 plus 10e to the half x. What I always like to do is draw the original graph. The original graph is e to the x. We're just doing a bunch of fancy stuff to e to the x. So this is y equals e to the x. We are doing multiple transformations to this. We're affecting x and we're affecting y. Let's focus on that point 1. Let's focus on this and let's see how that moves. According to the transformations, to the y values, I am timesing by 10 and I'm also adding 6. Okay, so to y values, you're adding 6 and you're timesing by 10. So if my y value is 1, times by 10 gives me 10, add 6 gives me 16. So that 1 moves up to 16. Okay? Now, if that moves up to 16, I've also technically got an asymptote here. That asymptote will also move. At this point, y equals 0. That's the asymptote. Times that by 10, you still get 0. Add 6, and now the asymptote has moved up to y equals 6. So when I draw, it looks something like that. Okay, the x value. We are doing 6 plus 10, f to the half x. So we are dividing all our x values by a half. Because it's a sketch, it's kind of hard to, notate that. So in this case, just having the 16 and the y equals 6 asymptote is enough. Okay, that is the breakdown of that question. If you feel like you understand it more and you want to give F another go, feel free to right now. If not, I'm going to go through F now. So we got y equals 100e to the minus x plus 10. Okay, so if e to the x looks like this, e to the minus x will look like that. But that point is still 1. Now, what are we doing to the y values? We're timesing by 100 and we're adding by 10. We've got two y values which we're concerned with. The first is that point 1 and the second is the asymptote, y equals 0. Both of them we're going to times by 100, we're going to add 10. So 1 times 100 is 100 plus 10 is 110. So this moves up to 110. 0 times 100 is 0, add 10 is 10. So the asymptote moves up to 10, or y equals. And then you draw something like that. Let me draw that a little better. Hold on. Something like this. And there you go. That is how you do transformations, and that is how you differentiate the e function.